Thank you very much. So this is my slide title, and I will talk about 3 Japanese sample return missions and its findings, focusing on reflectance spectra. So next, please. Okay, so in my talk, I will start with an overview of Itokawa spectral results and also try to find some linkage or some difference discussion between first C-class asteroid Ryugu, Hayabusa 2 sample return mission target, and also we already have several samples, and also another type, Martian moons, are really dark small body too. So, and also it has several previous spectral data, and in future MMX mission will have more detailed data and also return the sample. So it's a good topic to take a look with you. Next, please. Okay, so first, Itokawa has been observed in visible and also near infrared range. And first, visible spectra showed really typical S-type asteroidal spectra, and also it's similar to, of course, ordinary chondrite. I mean, it has a red slope, meaning like positive slope with wavelengths, and also it has a significant absorption marked as red region in the right-hand side spectral diagram, and it's due to Fe2 plus and existed in olivine and pyroxene at the surface of Itokawa. Next, please. Thank you. And also, it has a good relationship with visible spectral slope and also visible and near infrared spectral reflectance values. So it indicates that more space weathered surface at the Itokawa shows darker and redder spectra. By contrast, fresher surface, less space weathered area showed brighter and bluer. It means less red slope spectra at the surface of Itokawa. Next, please. One more effect was on the absorption band depth. So more space weathered region has shallower silicate absorption band. So here's a short summary, but Itokawa as S-type asteroids have shows really dichotomic spectral properties in reflectance, spectral slope, and also band depth variations. Okay, so next, please. Itokawa's results show really good space weathering trend on the surface of S-type asteroids. How to say, like determined by visible to near infrared spectra. Itokawa shows darkening, reddening, and also band weakening trend. And such space weathering evidence was determined also by sample analysis, showing amorphous rims, nanophase iron particles, and nanophase sulfide particles, and also blister structures at the very surface of Itokawa grains. And such Hayabusa results were also supported by previous telescopic observations and also ordinary chondrite analysis. Also, several laboratory experiments using olivine pyroxene powder samples show nice spectral changes if they simulate the space weathering effects using pulsed laser irradiation. Okay, next, please. So here's the Hayabusa 2 target reviews part. Next, please. Thank you. So Ryugu was also investigated by visible multiband camera ONCT and also near infrared spectrometer NIRS-3. Both are on board Hayabusa 2 spacecraft. And Ryugu's surface has really dark and rocky surface if ONC data we see, but the spectra taken by ONST and also NIRS-3 were really, how to say, like homogeneous, dark, and featureless, but except for 2.7 micrometer band. It is due to OH in hydrosilicates at the surface of Ryugu. But one interesting point, and also different from Itokawa, Ryugu has really homogeneous spectral global properties, like shown in the upper right figures in near infrared image, not image, but like map. So next, please. So by contrast, Ryugu has quite a homogeneous surface in several spectroscopic characteristics. Reflectance and spectral slope are quite stable, and also band depth there is, but the variations are really small, especially compared to Itokawa's case. Okay, next, please. So focusing on Ryugu's OH absorption band, if we take laboratory data using a returned sample from Ryugu, we can see really clear difference. It means OH absorption band at 2.7, we can see in the left hand side graph. Laboratory sample has really deeper absorption, like 2 times or more deeper than in-space data. But other properties like spectral slope and reflectance are quite consistent. And when we compare, of course, Ryugu's observation data and return sample analysis data, and also several carbonaceous chondrites data for simulating using laser radiation experiments and also solar wind simulating, ion implantation experiments, the data show, if we consider all the data included, such only difference for absorption band and stay other properties consistent. The most effective is strong spatial weathering effects on the Ryugu in-space surface. Okay, next, please. Thank you. So, how was the space weathering process at the surface of Ryugu? So Moroda et al. Estimate that current Ryugu's equatorial region were refreshed at certain point. It means like several tens of years ago after Ryugu's formation. The Ryugu was moved to its current orbit, and at that moment, fresh materials were exposed. And we can set a kind of start line from here to consider the space weathering process at the Ryugu's surface. And also good point is Ryugu's sampling sites are equatorial, which 2.2 touchdown sites are there. So from that point, 2 major space weathering processes, solar wind implantation and also micrometeoroid impacts were processed. But first, around 10,000 years, solar wind implantation has been saturated, and also micrometeoroid bombardments were still ongoing. So at this moment, current Ryugu's surface spectra should show the how to say like mixed results caused by saturated solar wind effects and also ongoing micrometeoroid bombardment effects.
10 minutes.
Well, thank you. So sample analysis using return review material also show both effects at the grain surface, like amorphous layer and also melted structures at the surface of river grains. Next, please. Thank you. So then to compare the Ryugu space weathering, not only Ryugu, but CV type space weathering compared with S type space weathering, we can consider based on laser irradiation analysis. So S type, the major component is olivine and also pyroxene. If olivine powder samples were used to laser irradiation experiment, the spectra were changed as well as Itokawa's case, redder, darker, and also absorption band becomes shallower, but the speed, how to say, not speed, but the effects are really low. So we need much time to make such a change at the surface of S-type. In contrast, CV class, the major component is phyllosilicates at the surface, and if we perform laser irradiation at the surface of carbonaceous chondrites, the spectra were changed, like bluer, darker. Also, OH band becomes shallower, but the change is really, how to say, like fast. So we need much shorter time compared with S-type to make spectral weathering effects of the CV class asteroids. Okay, next, please. So final part, let's focusing on MMX target Martian moons. JAXA's Martian moons exploration mission will perform sample return from one of Martian moons, Phobos, but also perform in-close observation for Phobos, Deimos, and also Mars. And the spacecraft will be launched next year, so we will get detailed data soon. Next, please. So, not waiting for MMX results, but previous spacecraft and also telescopic observations were obtained nicely Phobos and Deimos surface spectral data. And we already know there are two spectral types. We say red unit and also blue unit. Phobos has both of them. Red unit means steep, larger spectral slope region and also less red spectral region, but they are really featureless. But there are still several possibilities to get some absorption bands as shown next and later slides. So next, please. Thank you. So recent observation by NOMAD spectrometer get shorter wavelength range spectra for, I think, both red and blue units, and it shows a nice steep slope for both of them, and also featureless. But one kind of a mystery or unveiled region is 650 nanometer. There is or can be an absorption, and they discuss how to say, there is a bump or some decrease of reflectance, but we don't have direct observation data, so it still unveils spectral properties or possibilities. Next, please. Thank you. Also, CRISM has good visible to infrared spectra already, and also blue and red unit has slope variations. Dimos also red spectra similar to Phobos red unit. But one more interesting stuff is around 2.7 or 8 micrometer region. If there is a absorption band at the surface of Martian moons, we can have hydrosilicates or something like that, but we haven't had such direct evidence up to now. But anyway, we already know there are spectral red versus blue variations and still open possibility to have several, but small, but several absorption bands. And it can have some possible causes, something like space weathering degrees variations or more physical property diversities at the surface of Phobos and also Deimos. Next, please. Okay, so compared with Itokawa, a bit difficult because we don't have direct close observation, but Phobos and Deimos has bimodal properties as well as Itokawa too. So we can have dichotomic properties for reflectance and spectral flow, and not yet determined band depth variation, but it's exciting to get such spectral global variation on Phobos and Deimos surfaces. Next, please. So this is final slide of my talk. First, Itokawa S-type asteroid and as a target of Hayabusa shows bimodal spectral trend in both visible and near-infrared ranges, and indicating S-type typical space weathering, darkening, reddening, and 1 micrometer band weakening. Also, Ryugu shows really homogeneous spectra. It's really different from Itokawa. Both has really similar orbit and surface age, but space weathering effects have been differently effective at the surface of both of them. And we can say space weathering on C-type asteroid proceeds more quickly compared to S-type. Also, Martian moons, Phobos and Deimos show bimodal spectra in the meaning of spectral slope, and they are almost featureless but still have some possibilities of absorption band existence. So in near future, MMX will reveal detailed spectral properties, also together with return sample mineralogy and much more detailed data. So that's all. Thank you very much.